speaker is Kai Schneider. And the title of his talk is on helical multiscale characterization of homogeneous turbulence. Hi.
Yoshi, thank you very much for the introduction. I also would like to thank the organizers for the possibility to present some work we did together with Frank Jakobitz from San Diego, with Wouter Bos, a former postdoc of mine, now working in Lyon, and Marie Fage, she is here. And we are going to use some tools. You can imagine what, maybe wavelets will be behind a little bit. So multiscale characterization of homogeneous turbulence. And here we are interested in helicity. So the helical properties of different flows will be studied. What we like very much doing numerics is homogeneous turbulence because it's very convenient. We can use spectral methods for computation. We have no boundaries. We can do Fourier transforms. And the different flows we are going to analyze here, so it's mostly flow analysis, is first for reasons of comparison a Gaussian random field, which is divergence free. Then we have isotropic turbulence, either forced or decaying, rotating turbulence, sheared turbulence, which is growing, and also rotating sheared turbulence. And in the second part, depending on time, maybe I show also some simulations where we imposed some initial mean helicity, and then we studied the helical properties of those flows. And we are interested especially in different spatial scales here. Well, previous work, many parts are missing. So, for example, Bob Kerr, he may complain we didn't cite him here. Maybe just to mention helical properties, that goes back to Bechoff, Moreau, and Moffat, and then many other people were studying that. What we are going to use here are wavelet-based statistics, what we did with Wouter and Lucas, and also with the Japanese. And the numerical simulations we are going to analyze have been published in these papers. So helicity, what is helicity? So if we have a vector-valued quantity, let's say velocity u here, we take its curl, and then we divide of the respective norms, we get the cosine of the angle between velocity and vorticity. And that is the relative helicity, which we call hu. So the relative helicity of velocity. Then what we can do, we can take, well, instead of velocity, let's take vorticity and the curl of vorticity. And again, we can define the angle between vorticity and the curl of velocity, which is equal to minus the Laplacian of velocity. And what is interesting, so this quantity has values, so it's a cosine of an angle between -1 and +1. So plus minus 1 corresponds to alignment or anti-alignment of the vectors. And in the case when the cosine is 0, that means both fields are perpendicular. So velocity is perpendicular to vorticity in the first case. And in such cases, we are also talking about two-dimensionalization of the flow. And just from the physical point of view, so the alignment or anti-alignment corresponds to some swirling motion, what we find. So as the relative helicities, we can define the total helicity. So we are just not normalizing our quantities. Again, for velocity u and for vorticity omega. And if we now average these quantities, hu and h omega over space, we can write down a transport equation or a balance equation. So the time derivative of the helicity of u is changed by the helicity of omega, and then depending, of course, if we have forcing terms or not. This equation looks very much like the energy transport equation. So here we have for energy, the change of energy, and we have dissipation on the right-hand side. But the major difference now is what we should keep into mind, that helicity is a signed quantity. It can be positive or negative. So now it depends, of course, if we get dissipation of helicity hu, if h omega has the same sign as hu or not. So that is the difference with respect to energy. Keep in mind, we have a signed quantity. And that is something we want to analyze a little bit. So that's exactly what we wrote down here. So we have signed quantities, and now let's keep in mind this vector identity. So if we take the curl of velocity, we get the Laplacian, so dissipation of energy, so Laplacian of velocity. And what can be shown directly when you take the mean value, if you compute this scalar product, you see that the mean value is always positive when you take these quantities. And that implies, finally, that concerning the signs of HU and H omega, we get a tendency that HU and H omega have a higher probability to have the same sign. So in regions where we have positive HU, we get also positive H omega. And that has been observed by Sanada in a PRL paper. And later on, Galanti and Zinnober, they gave arguments that this tendency also holds for the relative helicities. Well, now let's go back to our flows. Just tell you again, random field and isotopic turbulence, rotating sheared and rotating sheared turbulence. We have no mean initial helicity first. And of course, if there's no mean helicity there's no generation of helicity. But we have to keep in mind, locally, of course, we can get helicity. But the mean helicity is 0. Now let's look at the probability distribution functions. So we plot histograms of HU, helicity of U, and helicity of omega for the different flow fields. For the Gaussian random field, of course, we have probability 1/2. Of course, we have -1 to +1, so the integral is 1. And you can see there's no preferred alignment as expected for the Gaussian random field. And the same holds, of course, for H omega. But now if you look at the different flow fields, for example, isotopic turbulence here in red and in green, either forced or decaying, you can see, well, we get some preferred alignment or anti-alignment here, or alignment between velocity and vorticity. If you go to growing flows like sheared turbulence or rotating sheared turbulence here in pink and in cyan, you can see, well, you get higher probability for two-dimensionalization. That means that velocity and vorticity are perpendicular. But if you look now again at H omega, we can observe in all cases, except for the Gaussian random field, that vorticity and the curl of vorticity are either aligned or anti-aligned. So we get much higher probability here. And now to come back to Sanada's conjecture, if we plot the PDF of the cosine of the angle between velocity and the curl of velocity, and using the vector identity I showed you before, we get a much higher probability that both quantities are aligned. And that implies, finally, that we have the same tendency that HU and H omega have the same sign. So already here for the Gaussian white noise, what you can see, well, we have a much larger probability that we have alignment between velocity and minus the Laplacian of velocity. Now let's look at joint PDFs to confirm this further. So if we plot the joint PDF between HU on the horizontal axis and H omega on the vertical axis, you can see, well, you get much higher values here that both quantities have the same sign. And similar results hold again for isotopic turbulence, either forced or decaying. You see we get some correlation of the sign. This holds also for the other cases. We're analyzing rotating turbulence, sheared, and rotating and sheared turbulence. So we have a strong correlation of the signs that the two helicities have some correlation. And that can be illustrated further. Let's look at some flow visualizations. So we are plotting here isosurfaces of vorticity, and we colored the isosurfaces either with a relative helicity of velocity or with relative helicity of vorticity. And to get the message, you can say, well, it's a big mess, I see nothing, but maybe the only message you should get out of that, in regions where we have blue, that means alignment of velocity and vorticity, we also have alignment, maybe let's look here at these places, of vorticity and the curl of vorticity. So that is just a graphical illustration of the joint PDFs we had. So in many places you have blue here and you get blue here. Of course there are some exceptions, but for example here you can see a different color, but statistically you get a higher probability that you have the same signs of both quantities. For example, if you take rotating turbulence here, where you get these columnar structures, your vortices aligned in the vertical direction, you can see again, well, where you have blue colors here for the classical helicity and here for the super helicity, you get a stronger correlation to have exactly the same sign. And again, similar message for rotating shear turbulence, where our vertical structures are inclined with a given angle depending on the rotation weight to the shear weight, what we have. That's the same message again. Now let's do a little bit of scale-dependent analysis. So we are using the wavelets here, orthogonal wavelets. Wavelets are well-localized functions in physical space and in spectral space. So it's a small wave, and you can decompose a flow field, for example, velocity, into a wavelet series. Wavelets have some nice properties. I'm not going to make a commercial for wavelets, but one nice property is that we have Parseval's identity for orthogonal wavelets, so you can compute energy in physical space or in wavelet coefficient space. You can then do some statistics. That means you can compute energy scale by scale, but you can also compute energy locally at different positions because your basis functions are local. And in addition, you have directions of your wavelets, 7 here in three-dimensional space, and you can also compute higher order moments. So now with respect to helicity, what we did, so we have a wavelet representation of our flow fields. Here we are only using the scale information. So in wavelets, when you like music, we only have octaves. We are always doubling the frequency in scale, and we can compute our flow field at a given scale. So here we have uj. We can do the same for vorticity, so we have omega j, and then you take the scale-dependent contributions here, and you can compute the relative helicity at a given scale j, what we are doing here. So you get relative helicity of velocity at a given scale j, and the same can be done, of course, for the helicity of vorticity. And now we can do scale-dependent PDFs. So reference case, on the left you see the Gaussian random field. Here we have the PDF of HU. Here we have the PDFs of H omega. For the Gaussian random field you see no scale dependence as expected. And for example here for the two isotropic flow fields, you can see at large scale, let's just take one scale j equal 3 here. For HU, you can see, well, it's more two-dimensional. You have a higher probability that at large scales, velocity and vorticity are perpendicular. When you're going to smaller scales, here, j equals 7, the sign color, we get stronger probability for anti-alignment or alignment. And if you go to the decaying isotropic flow, you get similar properties, but the two-dimensionalization is less pronounced. That depends probably on the forcing. And for H omega, well, again, small scales are aligned or anti-aligned. So you can do scale-dependent statistics. Also for the other flow fields, here you see more striking differences. Again, on the top, we have PDFs of HU, on the bottom, PDFs of H omega. And you see at large scales, well, you get a bump around 0, so you get two-dimensionalization, while at smaller and smaller scales, you get higher probabilities of alignment or anti-alignment, depending, of course, on the different flow fields. I'm not going to detail all this. Now, to come back, well, to flows, just 1 minute with initial mean helicity. So again, we have our transport equation, and now we impose some initial mean helicity using helical modes, the helical mode decomposition, also called complex helical waves, eigenfunctions of the curl operator. So in Fourier space, that's very convenient. You have your velocity field. You can decompose it into two basis vectors, which are eigenfunctions of the curl operator. These are related to the Cryer-Haring basis, so it's just a linear combination in spectral space. So you're working on a sphere in Fourier space, and you can represent your divergence-free velocity fields directly in Fourier space nicely using the algebraic identity that the field is perpendicular to the wave vector. And now to impose mean helicity, it's very simple, because you have your representation with coefficients xeta 1 and xeta minus 1 in your helical basis. And now the only thing to impose initial helicity, you play around with the coefficients. You have to change the strengths of the coefficients, and then you get fields either with no helicity when you are not changing the parameter alpha. So for alpha equals 0, you get very helical fields with +1 if you take alpha equal plus or minus 1. So you just keep one helical mode, and then you can switch between the two representations, and you get some initial mean helicity. Then you can look, of course, at the decay. So evolution of kinetic energy, what you can see here for flows without mean helicity in black. It's for sheared turbulence, and the initial helicity is decaying. So once we have positive helicity, once we have negative helicity, and you see fast decay, and the same holds also for the helicity of the vorticity, called here superhelicity. So we have a fast decay, and now what changes in the flow dynamics when you have flow with initial mean helicity? Well, what is changing is the dissipation finally. So what you can see here on the right hand side, difficult to read. So the production term is not changing, but the energy dissipation is changing depending how much mean helicity you are imposing on your flow. So you have a parameter to change, to modify the dissipation of your turbulent flow field. Now we can look at the PDFs of relative helicity. So when you have mean helicity in, your PDFs become skewed. So here we have the PDF for different values of alpha, our tuning parameter. So the one with alpha equal 0, we have a symmetric case, and you can see, well, the probability is changing depending on the initial mean helicity, and that can be quantified further by looking at the skewness, so the third order moment divided by the second order moment to the power 3/2. You can see we get a linear dependence of the skewness depending on this parameter alpha. And well, again, Sanada's conjecture. So let's look at the PDF of the cosine of the angle. That is not changing when you are changing the initial mean helicity. So you get the same probability function for the cosine of the angle between velocity and the curl of u. And of course, well, if this is not changing, we get the same or very similar joint PDFs. The only difference is they become skewed now when you are playing with your parameter alpha. And if you illustrate that visually, again, looking at isovorticity colored with relative helicity, HU, you can see, well, here it's more blue, here it's more yellow, because here we have negative helicity, here we have more positive helicity. So you can see the structures look still very similar, but we are changing the way how the vortices are turning. So you can play around with this parameter, but the topology is not changing. And now you can do some pseudo animation between the helicity, so HU and H omega, and you see, well, in places where you have blue for HU, you have places of H omega where you have the same color. You can do that scale dependent. Maybe I skip this. That is rather technical, so you can do this analysis again now with initial mean helicity. The information is the same, and I'd like to conclude. So we studied helical properties of homogeneous turbulence with and without initial mean helicity. Well, we've seen that depending if the flows have growing or decaying kinetic energy, the behaviors of helicity are changing. So we can see that we have distributions of helicity which show two-dimensionalizations for the decaying turbulence, while for shear turbulence we get alignment or anti-alignment. And finally, the scale-dependent analysis show that we have a trend for two-dimensionalization at large scales, while at small scales we have helical motion, and we have a strong correlation between the signs of helicity, of velocity, and helicity of omega, in particular at small scales. And if you're interested, there are 2 papers, one in PRE last year and one in Journal of Turbulence, which is in press. So thank you very much for your attention.
I'm sorry, I didn't introduce all authors of the paper. Besides Kai Schneider, Jakobitz, Voss, and Fudge. Sorry. And yes, any questions?
If you were to set out to deliberately set up a flow where the 2 helicities are of opposite sign,
Yes.
is there some way of doing it other than just randomly searching for it?
You mean to construct just one vortex with an imposed helicity? Because here we have a bunch of vortices, and then we are just doing a decomposition in our helical modes, and we say, well, if we retain this helical mode, we get positive or negative helicity, but it's still in a statistical sense.
Yes. Is there some way of deliberately finding a
I
flow?
think that's a possibility to construct vortices with a given helicity. I think Yoshi, he did some work. You even designed a program when you were visiting Marseille in Paris. There is a program existing where you can construct one vortex or a bunch of vortices with a given helicity.
In many simulations, of course, regions of high vorticity or mean square vorticity have been found. Now, is one of your conclusions that such vortices, concentrated vortices, are usually helical in character, either one way or the other?
Yes.
That's really quite important.
Because when you look at the visualizations, and it's exactly what you said, we have regions of high entropy, so high square of vorticity, and you can see most of the vortices are either show strong alignment or anti-alignment, but there are no regions where you have gray colors here, so either it's blue or it's yellow. So that means we have cosine plus or minus 1. And that is generic for all the flows we studied. So it's not only for shear turbulence, also already in isotropic turbulence we get this behavior.
Yes, sir? Okay, that's not.
Just a technical question. How do you make the statistics? Do you choose a certain point in the flow and you...
No, we take all points in the flow. So
all
we have
points in the flow. So it's not continuous, it's discrete.
No, it's discrete. We are using histograms. So we have 256 points in each spatial direction here for these simulations, or 512, some of them. And then we are just counting, we are just doing binning. So for each grid point, we sort where it belongs to. And the PDFs, typically, what we showed here, are using 100 bins. In most of them. For 2D, it's a little bit different. For the 2D joint PDFs, we have, I think, 50 in each direction.
Okay. So